Welcome everyone to the third session of ITC Peer Public Talks. The title for today's talk is Perturbative Color Moduli Inflation. The speaker is Noshin Fedor Sharma. She completed her undergraduate uh, degree from Kola University in physics, and she also completed her master's degree from alma mater Studiorum Università di Bologna,
Bologna.
Italy. Okay, so you have the stage.
Okay. Hi, everyone. So I'm not saying good morning, good night, or anything because good evening, because in my time, I think everyone's time is very different from everyone's. So, okay. Hi. So, as Sami said, that I completed I'm Noshin Fedor Sharma, and I completed my master's recently from University of Bologna. And there, I'm jumping to my topic. Okay, there in my master's, I did my thesis in string inflation. So, like in string theory, and okay, I'm not what I did work and also in this in my masters and also in the paper of mine. Uh, I'm not going to go very deeper mathematically because like it's a very mathematically rigorous topic. So like it will be very if someone from this conversation that we are having today, if someone is not having the knowledge about quantum field theory, general relativity in depth, then it will be very hard to understand the math. So I will give the I will try to give the conversation in a very theoretical base, okay, not very in depth. So after my master's, I did a research which called perturbative color moduli stabilization, inflation. So here, what we did, but before I give some jump into my work or give some conclusions about my work, I will actually tell about the backgrounds that why we do that and what's our actually motivations behind this work. So if I start, then okay. I guess if people are already watched Big Bang Theory, the series, then maybe from there they already heard about string theory, as the Sheldon was obsessed about. The character Sheldon was obsessed about string theory and all. So yeah, it's sounds very fancy, okay, but it's not not that much, but yeah, but it's interesting, okay. um I'm not demotivating, but it's very tough job to do. uh, uh I don't know how I did it, but somehow I did. And it's interesting, that's actually motivates me the most. So and also how to say also for maybe a little bit of fancy, uh, from this fascination maybe I did it. Not hiding anything. So okay, so why we are talking about inflation, and why when we're talking about inflation, then it's come out that okay, the beginning of the universe topic is comes out from it. So we all know about Big Bang Theory. Okay, so we know that in general, if we have to say that the universe began with a very tiny hot soup kind of thing. Okay, and then it was incredibly dense point at the beginning. Okay, began at least the start of the universe start with that point of view. As a scientist, actually predicted that with the base of the theory. So theory is kind of a thing, which you can mathematically maybe prove it, or theoretically you can say a lot of things about it. But for math, but experimentally till now, it's not like you can no one found it experimentally. So like theory is that thing. So Big Bang is a theory, and inflation is also is a theory which come after the discussion of Big Bang. So when uh, the Big Bang theory like proposed, then there's actually how to say okay, cosmic microwave background radiation observation actually saw that uh, from that observation actually it can be shown that the universe become so vast, and it's so smooth, like it's how to say that one thing is connected with uh, another thing, but the two things is very far from each other. So how they will connect it? In the case of like temperature, their temperature is also matching, and also when in the CMB data you are collecting two different light years distance materials point of view you are taking, then both of their data are matching. How they are matching? Okay, and how universe is so like geometrically flat? Okay, that kind of question arise from the CMB observation, and the Big Bang theory it's actually fails to answer those kind of questions. It's called horizon problem and the flatness problem that I already mentioned, the two problems. There's other problems also, but I'm just mentioning these two problems. So then the physicists actually arise another theory, is inflation theory, which proposed that which actually try to solve this a problem, which till now is a question for the scientist, that why, how did it become so fast and so smooth? So inflation is a process which try to answer all of these questions. So how it actually did it, because inflation is a moment, a very tiny moment after the Big Bang, very tiny moment, and it's a very rapid and exponentially uh, like uh, expanding moment after Big Bang. It's maybe 10 to the power minus 39 or 37 kind of nanosecond time of that. Okay, very tiny moment. So it happened. It placed inflation. So inflation possesses a moment of rapid expansion, stretching space itself in a tiny fraction of a second. Okay, this early expansion explains why distant regions of the universe look so similar, which is the horizon problem. So they were once very close together. In the time of inflation, the distant particles was very close together, so they exchange their data. That's why now in this point, when the distance points are we are measuring, then it's we can excuse me. Okay, then we can actually then actually we can find the solution of CMB by the theory of inflation. That inflation give us the solution, that how the in that tiny second, nanosecond, or in the tiny time lapse, they actually exchange the data of each other. And also in that tiny sessions, how from in that tiny session we came out of 3D, like our world is why it's 3D or 4D if you're counting the time and all. And how the standard model particles are built up, and all the things, all the symmetries and all the things happen within this inflation and after the inflation. Okay, that we see our universe right now, how this way inflation is actually giving us the inflation theory, if you are considering, then it's actually giving us that answer of all the questions. Okay, but okay, again I'm saying that it's experimentally till now it's very not viable that we are finding all the answers, but uh, theoretically, mathematically it's very rigorous. When you are going to study about this, you will see that mathematically it's very fascinating that how those things are mathematically actually was connected with each other, and mathematically you can also like go by proving that. So like it's just maybe we are hopeful, we physicists are hopeful that we in future, maybe with very modern colliders, maybe in future we can find something which can answers all of these theories. Maybe it will take time. I know like string theory is taking a lot of time, but I hope, like we just can hope and do the math. Okay, so hopefully someday. So one problem that inflation gave, and also the flatness problem. Also, like when you see the universe, you can see that it's geometrically very flat. Okay, so how geometrically, like how is that possible? That why it's very uniform? Why it's this much smooth? Okay, inflation is giving all the answers. Okay, tiny quantum fluctuations magnified by inflation become the seeds of galaxies and cosmic structures. What I say, that what the universe that we are seeing today, it's like the galaxies, the cosmic structures, all the answers are hidden, like we found from the inflation, where the tiny quantum fluctuations like by inflation occurred, and it's the seed for those galaxies and all. Inflation helps turns the chaos of the beginning into the quiet order we observe in the universe today. The same thing that I said. So, okay. So now we have that, okay, for solving the very big problems of the universe, we have a theory, inflation. Okay. And now for proving it mathematically, we need a like viable inflationary model. So for proving that, again I'm saying here that I'm not going very in depth of the mathematics. Just I'm saying that here also in this slide you can see, I'm trying to show you the criteria that actually needed for building an inflationary model. Okay, so like here I just point out the criteria, where it's called, the first one called eta problem, and which must have to be less than 1. Okay, this is the Hubble constant. Okay, by like here also you can considering, here we are considering the Hubble constant, and if we are considering the slow roll conditions. Okay, so inflation for, okay, and if I'm seeing here the diagram, then you can see, if you are taking a scalar field, let's say it's phi. Okay, so if you are measuring the potential v phi of it, then if you are taking the like graph of it, then the slow roll, you see this point here, I'm sorry. You see this point here, where it has to be very slow roll. Like in that like tiny moment where the inflation happened, it's it have to be like not going very it have to be exponential. It can't do like very rapid. It is rapid, but it can't go like that. Okay, like from one point to like one point it's here and one point it's here. It can't be like this. Okay, because scientists, if you have to if the inflationary model have to be like the seeds of the galaxies and constructed the like cosmic construction, then there should be a time zone which have to be maintained, and slow roll inflation for that is very needed. So the inflaton, if we are inflaton as a scalar field, if we are considering, which we called inflaton, and in the string theory we are calling it moduli. We will discuss it later, a few minutes later. So like in that case, it's like here you have to be considering the slow roll inflation. Okay, so it has to be like slowly but exponentially, and it will have to be rapid. Okay, uh, the time zone is rapid, but it's going very slow. I know it sounds very confusing, but if you mathematically see it, you can understand that how we can count the potential here with the base of the scalar field. So if we are considering, so if we go back to there, so here the slow roll conditions must have to be the eta problem. Okay, sorry, epsilon problem is that one, and there's the eta. So eta also we are counting with this, where v phi is the potential, and the double derivative of potential will be v phi, like dot 5, and it also have to be much less than 1. If these two criteria, if someone is giving in future, some physicist will giving another model which have to maintain the criteria of inflation, then these two criteria must have to be fulfilled for sustaining the inflation. Okay, here I already said that for inflation to be sustained, the inflaton field phi must evolve slowly along its potential. So it has to be less than 1. So just keep in mind that these two criteria we have to be maintained. And okay, then after exit from inflation, we are having a reheating like phase, and then we having the expansion of it. And okay, there's another criteria is the tensor to scalar ratio constraint. It's also we are measuring it we are defining it at with r is equal to 16 epsilon is this one, the accelerated expansion. So this is the criteria for building the inflation. And now what string theory is doing? String theory is actually uh, when you are trying to build a model based on a string theory, build an inflation model based on a string theory, then it's called string inflation. Okay, so in string inflations, actually, what is, firstly, I'm giving you that what is the string theory. String theory is, we know that quantum field theory. Okay, we know that considering the fields and everything, but we know also the gravity. But when this quantum field theory and the gravity is connected together, okay, and we are finding some theory based on connecting this together, then string theory is kind of the theory which actually can give you one combination of this quantum field theory and gravity. Okay, so so here we have two theory, inflationary model and string theory. When based on the string theory, you are trying to give the answer of the inflation or try to build a model of inflation, then we called it string inflation. Okay, here I'm saying that string inflation aims at embedding inflation model within string theory to ensure their stability, addressing UV sensitivity, fine-tuning issues, and constraints on the inflation potential. Okay, so why we are doing this? Because like till now, string inflation is one of a kind that can build the inflation model which is like very, not very near to the experimental data, but at least can be viable. Okay, so again, I'm saying that it's a theory. So our target is to how close we can go to the experimental data till now we have, or like we are giving based on the theory some criteria which maybe the future colliders can like can help us to prove that. Okay, so all the things we, for building up a model, all the things we have to be considering in our mind. So that's why string theory is kind of a thing which actually mathematically you have to considering a lot of data when you are doing it. So it's like mathematically it's very rigorous, and like uh, physicists till now, a lot of physicists are doing this because when you are doing this string inflation, string theory, cosmic inflation, it's like giving you the satisfaction in mathematically. If you are considering, it's like very smoothly you can do it, not smoothly, not easily, but at least you can like give some answers. So for this reason we are choosing, we are embedding actually inflation models into string theory, so that we can actually answer a lot of things: the stability, UV sensitivity, fine tuning issues, and of course the inflation potential and all the inflationary criteria that we already saw. So it also provides a framework to test high scale physics and ensures proper energy transfer during reheating. Okay, making it a crucial tool for understanding early universe cosmology. That's our actually the string inflations provides like this kind of final things, that early universe cosmology, our main basics is to understand the early universe cosmology that we are dealing with. So it's actually the crucial tool for understanding that. For string inflation to work, the extra dimensional fields, which we are calling moduli. So uh, I am clearing this point a little bit later in the like following slides. We can see that how come the in string theory we are considering like 10 dimensions, or some models till 11 dimensions. We can like dimensional fields we can actually consider. Why we are considering, and like how I'm giving the like physical intuitive answer in the following slides. But mathematically, if you're seeing, it's also like it will be like you can take one class for like providing the information why it's actually seeing. So how far I can do it, I provide the things in the following slides, but we will see. So for string inflation, till now just know that, okay, string inflation considers a lot of extra dimensions. Okay, not just our 3 dimension or 4 dimensions we are observing now in today. So like, okay, for string inflation to work, the extra dimensional fields, which we are calling moduli, must be stabilized to prevent them from interfering with inflation or causing instabilities. This point is very like important, because till now what we are doing in string inflation, what I also actually do in our paper, it's also we are doing to stabilize the moduli. Okay, moduli is the extra dimensional fields that we considering for string theory, and it must have to be stabilized. Okay, otherwise it if we are not stabilizing, then the criteria that we already got from the viable inflationary models, it will be ruined and causing instabilities. So that will for starting the string inflation to think about, you also have to always think about compactification of the extra dimensional fields, which will cause the moduli, and this moduli also have to be stabilized. So this is the criteria. And also at the same time, the inflaton mass needs to be within the right range. Here is the range where, like, here if you see the first one is the Planck mass. So the Planck mass that actually experimentally we are having till now. So for the mass range to be accurate for the inflaton mass, which is the last one, it has to at the same time it needs to be very very less than the Planck mass. Okay, so we can see the range here. I'm not going very depth because in my model we are not actually considering that much of this mass consideration. So okay, for moduli we already okay, now moduli is the second. Okay, for string theory and extra dimensions that I already mentioned. So extra dimensions are the fundamental to string theory. Okay, where we are considering 10 space-time dimensions, or for M theory, there's another theory where it's 11. Okay, 11 space-time dimensions. For mathematical consistency, if you're seeing for beyond 4, we observe 3 space plus 1 time, of course. So in string theory, we require 10 space-time dimensions, where the other 6 are like we are compactifying. So what is compactification? Compactification actually the hides the extra dimensions. Okay, well, we know that 4 dimensions we have, and the other 6 we are actually curled up within the 4 dimensions. And for why it's needed? Because uh, when in the case of inflaton, the scalar fields we are considering for the considering the model for string theory, this curled up fields actually give us the consideration of the scalar fields, which we call in moduli, which is actually helpful to find out the size and the shape of the space, and which is for after we find the compactify space size and shape, then we can actually connect it with the viable inflationary model with this data. Okay, that's why string theory we considering the extra dimensions. Okay, so here it's saying that the extra compactification hides the extra dimensions. So compactification literal meaning is the we are considering the 4, and the other 6 are actually curled up or hiding in the 4 dimensions. Okay, if you considering to say in an easy way. So the extra 6 dimensions are compactified into tiny curled up shapes. Okay, which also in string theory we are considering the Calabi-Yau manifolds, where we are considering some manifolds where why I didn't put the picture. If I put the picture, you can understand that we are considering the setup where actually we saw how the strings are dimensions are curled up into this manifold. So too small to detect directly, but they affect physics at low energies. Okay, geometry shapes particle physics. The shape and the size that I already mentioned, that this kind of geometry, like compactification of the extra dimension and everything, it actually shapes the particle physics. Okay, when we are trying to answer all the particles, standard model particles, how it comes and how it's connected with gravity, then the extra dimensions requirement are automatically comes up. Okay, so that's why it says that geometrically shapes particle physics. The shape and the size of the compactify space determine key physical properties: particle types, force strengths, So they are also like, as there's also gravity, so and also the particles are connected with each other, how within this extra dimensions and with the compactifications it's connecting, it's already like the answer for the extra dimensions requirement. So moduli fields arise from this geometry. As I said before, each degree of freedom in the compact space corresponds to a modulus field in 4D controlling things like size, shape, and coupling. These moduli are central to string cosmology and inflation models. So when we are considering the compactification, so for answering the size, shape, and the coupling, like moduli fields comes up. Okay, and this moduli fields actually the central to string cosmology and inflation model. So for inflation models and for string inflation, it's moduli is the most important, like modulus fields is the most important thing what we are going to like experiment or like we are going to research about it. In our case also we are doing the same. So moduli, it's actually the natural inflation candidate. The shape and the size of the extra dimensions are described by fields called moduli. I already mentioned it. And moduli are natural inflation candidates. Actually, it's the scalar fields from extra dimensional geometry are ideal for driving inflation because they are already present in the 4D effective field theory of string compactification. Okay, so if we have to find the inflation, as we are considering that, okay, we all, today's life it's viable that we are considering, we are seeing, we are present in the 4D. So like effective theory, field theory is also considering the 4D. So for this reason, these scalar fields, when we are considering also extra dimensional geometry, so comes up with the idea to driving inflation within the 4D effective field theory of string compactification. So inflation can occur when a modulus field, like a volume modulus, a brane position, or an axion, which you can ignore. Just to consider the modulus field as the simple scalar field. Now we are not going very depth about the volume modulus or brane positions or all. Slowly rolls down a potential. So we already see that we have to find out the moduli. So from this moduli field, we will find a potential which will, of course, which have to be slowly rolls down. Okay, which is the criteria for inflation we already saw. So here the for considering the modulus field, if we are considering phi, derived it as phi. So for v phi, it have to be flat enough for slow roll. Of course, slow roll is the main conditions for our inflation. All other moduli must be stabilized during inflation, otherwise they would interfere with inflationary dynamics or spoil the 4D effective field theory. So as we already discussed, that must it have to be stabilized. And stabilization is the must needed thing that now all the like string theorists actually are doing. Okay. So what is moduli stabilization? Moduli stabilization is essential in string theory to generate a potential for moduli, okay, preventing massless modes that could lead to a long range fifth forces and instability. Uh, okay, so make it very easier for that. So when considering that there's a volume you are considering in, okay, and when other, okay, in the volume we are considering that the it's in 4D, but when the other extra things like 6D we are considering and other particles also the gravity we are considering here. So when we are curling up all the things into this volume, then the volume actually changed. It should be changed. But as we are considering the four-dimensional, so we have to be maintaining this volume. So for maintaining this volume, and if you are pushing all the other things curled up into this, I'm sorry about the sound. Maybe. So if it's like if you are compressing it, then it should be changed, right? The volume should be bigger, or it should be like a stretch out or something. But we are not considering that. We have to maintain the volume. So for maintaining it, some stabilization, some corrections, some things are needed. Okay, so moduli stabilizations are needed, and we are considering also the corrections in the like which corrections actually help moduli to stabilize. We will see later in the following slides. So there's a lot of mathematical things I said, but okay. For like mechanisms like fluxes, perturbative corrections that we are like we did the research about in this paper with the perturbative corrections and non-perturbative corrections, like help achieve a stable vacuum, ensuring a consistent low energy theory and influencing supersymmetry breaking and cosmological evolution. Just not to go into all of these words, so don't puzzle yourself with all of the words. Just remember that for the corrections that we needed for helping the moduli to stabilize, there's a three: fluxes, perturbative and non-perturbative. Okay. And two main moduli stabilization schemes are large volume scenario and KKLT. Those are the KKLT is the name by Kachru, Kalos, Linde, and Trivedi. Okay. Maybe in the case of Kalos, I'm not sure about the pronunciation. Sorry about that, but yeah. So KKLT. Okay, so in the case of flux, large volume scenario, we are considering flux, perturbative, and non-perturbative corrections. Okay, and in the case of KKLT, we are considering flux and just non-perturbative, not perturbative. Okay, so um, for as we already mentioned, that quantum corrections are needed, mostly non-perturbative corrections and perturbative corrections are needed for moduli to be stabilized. So what is actually quantum corrections? In classical physics, if we are seeing that considering, then fields and particles follow a smooth, well-defined path. Okay, but in quantum physics, everything fluctuates. Okay, even in empty space. Okay, there are some fluctuations that are like present in quantum physics if you are considering the path of the fields and the particles. Okay, it's not smooth, but in classical physics is different case. So this constant fluctuation uh, shift the behavior of fields. Okay, it's actually, of course, if there's any like disturbance in the like path is of the particles, then of course it will change the behavior of the fields, but it's very subtle. Okay, it's very subtle. The subtle shifts we can see, it's very maybe tiny or very like infinitesimal fluctuations we can see. So those are the quantum corrections. So if a scalar field like inflaton or modulus we are considering has a classical potential V phi, quantum effects modify it slightly. So in the classical physics, if you are seeing, you just have the classical V phi, the potential. Okay, but in considering of these fluctuations in quantum physics, so you have to consider also the quantum corrections. So these fluctuations are actually needed for like understanding the behavior of the field. In the early universe, energy scales were enormous. quantum fluctuations could significantly reshape the inflaton or moduli potential. So as we are considering all the things, we are considering all the scenarios of the all the fields, particles, and like coupling, everything we are considering from the early universe. So the fluctuations that we are actually considering, it's reshaping the significantly reshapes the inflaton or moduli. Okay, basically the fields actually, it's effective. So this affects whether inflation occur, how long it lasts, what patterns appears in the CMB and the stability of moduli fields. This actually affects these quantum corrections. This, if you are saying in other way, quantum fluctuations actually affecting all of this, the inflation, the stability, and what patterns appears in CMB, all the things. In string cosmology, there's a two types of corrections contributions we are considering or needed to stabilize moduli. Uh, for realistic inflationary potentials. One is non-perturbative corrections and perturbative corrections. Here we in our paper we are considering perturbative corrections because non-perturbative corrections we already considered, and it's not actually giving us uh, like without fine tuning, it's not actually giving us very smooth results or very viable results for eta and epsilon problem. Okay, eta problem that we are having. We saw eta. I just told you to keep it in mind, the inflationary uh, criteria, model criteria. So we are facing eta problem if we are considering non-perturbative correction. So this is also a topic of research till now, that how non-perturbative corrections actually are, we can build something for doing moduli stabilization with these non-perturbative corrections. So we are considering actually perturbative corrections here. So perturbative corrections, now I am actually giving you a lot of mathematical basis, but don't dilute yourself around this, but try to just understand a little bit. I am not expecting all of you are in this mostly who are from like a bachelor or master's first year or something. I'm not expecting a lot. Of course, if someone is not doing theoretical physics, it will be like hard to understand this mathematics, because it's if I someone is doing some experimental physics or applied physics explanation, maybe it will be must be hard for me. So don't dilute yourself with the mathematical rigorousness here. Just try to just grasp the basic. I am also trying to give all the basics. So till now, what we saw, it's like the basic, that what actually motivates me or the physicist to do the work based on this string inflation. I hope I somehow explain well. I hope so. I hope you guys understand a little bit. Okay, so quantum corrections, like perturbative corrections, here it's actually these corrections are arise from alpha prime effects at tree level in GS and loop effects in the string worldsheet. So the leading corrections to the 4D tree level Kähler potential. Okay, so mostly the Kähler potential is like this. Okay, and if you are adding corrections, so the corrections look like this. The corrections will be like this, like we already saw, sorry, here. Like V is the classical and then the plus the quantum correction. In the same case here also, this is the actual form of the Kähler potential, and those are the things for the corrections. And these corrections are coming from tree level alpha prime effects from the tree level and loop effects in the string worksheet, which I'm not going to discuss. Like just to know that that's how you can so okay, one more thing. When we are considering like string theory, like other potentials, we are for having the f term potentials, which is the main potentials. So for having that, we need Kähler potential, two potentials. Just remember the name: Kähler potential and super potentials. Okay, so perturbative corrections actually affect the Kähler potential. Okay, and we are taking the Kähler potential in that form. And non-perturbative case, with like firstly, those non-perturbative corrections actually arise from ED3 instance and Gagino condensation on D7 branes, which correct the 4D3 level flux generated superpotential. So non-perturbative corrections are correcting the superpotential in that way, and uh, perturbative corrections are correcting in that way. But perturbative corrections also like have some effect on non-perturbative, on superpotentials. But in that case, we are not going in depth. Just it's like it's depending on the model to model. Okay, so in our case, we are in general we are taking the superpotential like as like W naught, not with the non-perturbative corrections. This is the non-perturbative corrections, which we, in our case, we are not actually considering. We just considered superpotential as W naught. And for our case, so we have a lot of corrections. With that, we have a lot of other corrections. It's this, those corrections actually are depending basis on different models. So in our models, we are, okay. And also, we already said that for discussing all of this stabilization and corrections, we have two schemes. One is KKLT construction and one is LVS construction, where in LVS we are considering all, like the non-perturbative, perturbative, and the fluxes, and the KKLT cases we are actually considering just the non-perturbative and the fluxes. Okay, so in our cases, we also can see that how LVS construction we are going to do. So in this, okay, Kähler moduli inflation. Now I'm going to my work of the paper. Till then, I just gave you all the data we needed to keep in mind. Okay, so Kähler moduli inflation, we can say blow up inflation. So now what we do, we embedded inflation within type 2 compactification. So we already know that what is compactification. Compactification is the like to made the all the 6-dimensional curling up to the 4-dimensional. Okay, so that is the compactification, if you remember. So there's a lot of type of compactification. So here we are considering type 2b compactification. I present first the model known as the blow up inflation. Okay, here we are considering two models. And from this two model, we find out multiple moduli stabilization. Firstly, I'm showing you how in our paper we are considering the blow up inflation. So for the volume that we are considering, in the blow up inflation cases, in the first cases of ours, we are considering this tau and this tau. So it is two moduli. Here we are considering multiple moduli. Okay, this is one and this is another. Okay, this is the big moduli, this is the small moduli we are considering. We know what is moduli. It's the scalar field that we are considering. And based on this scalar field, we will find out one potential. Okay, this is the potential that we found. Okay, I'm just reviewing the thing. So based on this potential, we will find, based on this moduli or scalar field, we have to find out the potential, and this potential have to maintain the inflationary dynamics or inflationary constraint that we already discussed. The eta problem, the tensor and scalar ratio, and all the things, spectral index, all the things has to be matched with the inflationary model. So here we are considering the volume in that shape with the color potential and super potential taking the form here, as I mentioned here. Sorry. Oh, okay. Here, this is the Kähler potential. This is the super potential. Okay, we already mentioned. So this our I already mentioned that those Kähler potential and super potential can looks different in the case of different models. So in our models, if we are considering first the blow up inflation, then our in our model case, the Kähler potential look like this, and the super potential will look like this. So if sorry, okay. So if we displace a small modulus far from its minimum, okay, for considering the inflation, so we have to consider a minima. Okay, in the case of what is called modulus, sorry, in the case of a small modulus, we have to consider a minima. I'm not going to talk about this minima a lot. So we will find the potential by considering this k and w. There's a for effective sorry f term potential like defining. We have a like a proper definition with the k and w, how we are counting considering this k and w, and how with the mathematical calculation continuation we will find this like case in the case of effective potential, and in the case of inflation potential it will be like this. Okay, now here one thing noticed that firstly, we are considering the big modulus and the small modulus. Okay, then we converting it for considering the minima. We canonical normalization. We converted it with tau phi. Okay, so here we are all considering here the tau phi. So you can see the tau phi, not the tau b or tau s. So after finding the k and w, and then after considering the canonical normalization, we normalize uh, this modulus to tau phi. Just remember this. We normalize this modulus to tau phi, and then we found out this potential. Okay, this is one of the like model that we consider, which is the blow up inflation. So keep the overall volume. We are keeping the overall volume fixed. Already I discussed why. Exponentially fat potential enables slow roll. I already told that exponentially flat potentials is actually needed for having the slow roll. So all of this consideration and canonically normalized potential, if we are finding, then we will find V phi as like this. Okay. Okay. And for considering the observational values obtained from this model that we actually consider, and we can find the spectral index, which is n, and the scalar ratio tensor, which is r, which is the needed for considering the like inflation model. Okay, so this is our cases. The like the r is in between this 0 to 10 to the power minus 10, which is also like matching with the constraints that we actually consider, and also n is in between that, which is also matches. So our main thing was to stabilize those Kähler moduli. Okay, and then considering the Kähler potential and the a superpotential, and then find out a V phi potential, which we canonically normalized potential we found. And then for observational values that we already observed, okay, for the inflationary dynamics, then these dynamics are satisfied. After considering all the values, we are finding those things which actually matches with our observational values. This model is subject to further corrections, adding to better phenomenological result. Okay, this model we are considering here, the second model of our perturbative Kähler moduli inflation. Okay, now we are considering from those other models to jump to this model for more sophisticated calculations. For our model, the volume is this, and where Kähler like K is equal to K naught plus this is the loop corrections, and Kähler potential taking the form in this way. Okay, we now our model, after influencing by the blow up model, we are considering the Kähler potential in this way. Okay, here is the corrections, here is the K loop corrections, how it looks like. Okay, and the super potential, as I said, we are considering this, and the effective potential we will find this. After canonically normalized, we will find like TS is equal to, like, we are considering the phi as the canonically normalized field now. So we find V is equal to this way, and the second case we are finding this. Okay, as we considering two cases here. So all of these cases predict matches with the prediction of the inflationary predictions. Okay, so here I like mistakenly wrote down case one. It will also with the case two. So with the canonically with all the, like, where is that? With all our main potential is this two potential, case one and case two. So for that potential, after stabilizing the moduli, we find out the two potentials, and we found the inflationary. If we are calculating the R and NS and the okay, E folding. Okay, it's right. No, I didn't mistake. Okay, and also we are considering the E folding. Then all of those data that we are having here, you can see the in this slide, actually matches with the inflationary predictions. So what we actually considering to find, it's fulfilled. Okay, so this is the conclusions. We've first considering blow up inflation, and then perturbative Kähler moduli, and then we find the multiple moduli stabilization. For after doing the stabilization of this, we find out the data for canonically normalized potential for case one and for case two, and then we match those cases with the inflationary predictions, which actually matches with our observational data, which is our which was our goal, and we fulfilled our goal. So this is the conclusions I'm shortly saying. So we actually trying to, so if all of the, not just the model conclusions, if I am saying all the conclusions here, that what I trying to say to you, that from Big Bang we are considering the inflation to try to answer the horizon and flatness problem, and for that inflation, it's actually giving us the answer of those two problems. And then for inflationary model, what criteria we have, and then for basis of this criteria, we find out we try to build up a model of string inflation, which is our main work to do. So string inflation, when we are considering string inflation, then there we have to consider the moduli and moduli stabilization, and there's a lot of model Here in my paper, I consider two models, blow up models and the perturbative color potentials, color moduli, which after finding all the stabilization, we find the data that we actually expected for having observational, for matching with the observational data and for matching with the inflationary dynamics. So yeah, that's it. I hope it's understandable, and thank you for listening to me.
Okay, so I have a question.
Yes.
Uh, can this model,
Yes.
uh, like the our previous session was about gravitational wave. So
Okay.
can this model mathematically, it's a theory, so can this model mathematically predict the primordial gravitational waves, the gravitational
Yes.
wave? Yeah.
Okay, so for primordial gravitational waves, there's also, okay, string theory have a lot of group. Okay, so one of the group is uh, uh, loop quantum gravity. Maybe in there also they actually considering the primordial gravitational wave. But till now, maybe in string theory, also in our models case, I am not sure. I can't say you properly, very confidently that you can consider. But if we can find out, we already find out the data for matching with the inflation, then if you're considering the reheating and all, then I think it could be possible, but I can't say properly. But in the case of loop blow up sorry uh, loop string model, sorry, LQG, loop quantum gravity, yes, LQG, maybe they are having some ideas about
Okay.
primordial. Yes, but it's there's a lot of string theory models where they are actually working with primordial gravitational waves and also with dark matter, dark energy. It's a vast field where I am just starting with just inflation model proof and how if you're considering in the early universe how we are taking the 10 dimensional, and for after inflation is ending we are going to the reheating phase, how in the end point my thesis work was that how in the end point uh, we comes up from 10 dimensional to our 4 dimensional. So our thesis work was related to that how actually our model supports the ending of the inflation, and how we actually find out the viable scenario that we are now in today's world, like a standard model particles, how we get also. So there's a vast actually idea. I'm not sure, but I can say that yes, maybe there's some people are actually working with it.
Okay, so when you say like you uh, in string theory you're working with like more than, let's say, 3 dimension. So if
Yes.
it's like 4 dimension, is it like three space coordinate and the other one is time coordinate?
Time.
And if you have like
Yes.
fifth dimension, then
Yes.
is that fifth dimension is like a space dimension or is like a
Yeah, we are
variable that?
considering. No, no, we are considering a space dimension because our
So,
Calabi-Yau models are actually considering one is just the time dimension that we are actually considering for the 4D, and the others are actually the space
so if you have
for
like
considering them.
11 dimension, then you have like 10 space dimension, the other one is the time dimension.
Yeah,
So
yeah,
what
yeah.
does it mean like to have like a fourth dimension in space, uh, physically
Uh,
for?
okay, it's like when if I'm saying you like shortly that how actually there's the Kaluza Klein. Wait a minute. Just I am searching the name because I'm very bad at remembering names. So I wanted to add this, but I felt like that okay, it's very like Kaluza-Klein theory. So there, they considered the like a five-dimensional scalar field where they started because they consider when you are considering the quantum field theory. Okay, when you are considering the uh, like uh, um, high energy particles with the gravity, it automatically generates for the coupling and everything. It's automatically generated the like mathematically, if you are saying, it automatically generated the higher dimensions. Understand? It's automatically generated. And Kaluza Klein theory, if you are interested to know in depth, or if you also want me want to discuss about it in depth, then we can another day we can also talk about the dimensions, Kaluza Klein theory, which is actually started for a
I'm
five-dimensional
sure,
scalar
like,
field.
can
And
you
then
like give you like like a I don't know, like explanation for like general people, like how what does the fourth dimension in space mean for us? Like, are there beings in those dimensions that we cannot see because I don't know.
no, those dimensions you can't see.
Mhm.
So okay, so
Do
in
we
string theory,
have experimental proof of those dimension existing?
nope, 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 till now no, it's just
Okay.
mathematics. So we are considering the okay, strings, right? We are considering strings. Strings is like we are taking the particles like strings, like normal strings you are considering. So all those strings are actually confined or curled up. Okay, it's very hard because I am doing one model which is like explaining all this with the D brain and anti D brain. It's very hard to make you understand. So okay, let's see that this is the wall. Okay, all the strings are actually curled up within this volume. Okay, and those strings are the particle, and those strings are like how to say the coupling. When you are considering the couplings of these particles with the gravity also, then automatically not automatically, mathematically is generated the idea of the higher dimensions.
Okay.
But it's not till now it's not possible to like experimentally see or experimentally finding those data.
I don't think
Okay.
anyone else has any questions, so
Thank
we
you all
can
again.
end our session here.
Yes.